Hi, it's Maker Geek and I'm Dan. We both know why you're here, so let's get on with it. This is an update on my electronic lead screw. What I want to do quickly is run through where we kind of left off. We have a control board, an encoder and a motor. I've upgraded the motor, but let's have a quick review of those three components and then we'll get into demonstrating what they can do. So, simple encoder, this guy reports 600 pulses per revolution. We have a 3D printed GQ pulley that just clips around the spindle and a belt. So spindle rotates, belt rotates, pulleys rotate, signals. This is set up to, in theory, give me 800 pulses per revolution, and that input signal is fed into an Arduino Nano. So we have a custom PCB, an OLED screen, some buttons, and we have inputs from the rotary encoder here. We have inputs from some end stops and outputs to the stepper motor. Let's go look at that. So this is the expensive end of the spectrum. Basically, this is the bit that costs the money. This is a servo type stepper motor. It's quite nifty. It has an onboard controller. So this came from Steppers Online, not a sponsorship. I bought this with my own money. But you feed it power and the step and direction signals. And not only does it move it, but it knows its own location and tries to hold that position and tries to recover if it stalls. And that's quite important for trying to make sure that you get a more reliable output. Previously, I just had a regular step motor, and if it had any kind of stall, then game over. There was no way to recover. So that's that. It's on a straight couple right onto the end of the lead screw. I just made this out of a chunk of steel. Pretty easy to make with a couple of grub screws just to hold it solid. I went with the straight through. Obviously you could just put in like a pulley setup. You could do a ratio. You can mess around with kind of how much torque and speed and blah 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 blah. But honestly, it's got enough grunt. The straight through couple was pretty easy, and this is a very simple and relatively wobbly 3D printed mount. But as long as the rotary doesn't change, that's all good. And at the back here, we have a fairly standard power supply. This guy is a 48 volt power supply. I bought a switch for it and 3D printed a little enclosure so that I could have a slightly nicer setup. But fundamentally, switch that on, the motor's on, everything's live. So the other thing that's upgraded considerably since last time is just the software. So bit of a small display, but I try and put a lot of information on it, which is useful for me, mostly in debugging. But what we have is our threads that we support, or our threads and finishing pass, basically what ratio of motion per RPM I want, which goes all the way up to 20 at the moment, which is ridiculously aggressive, and only for one of the modes that we'll get to later. The other thing that I have updated, you may have caught me say earlier that in theory the rotary sets out 800 pulses per revolution. In practice, that's a 3D printed pulley. There is a certain amount of error, so one of the improvements I've made is a calibration mode. All I did to calibrate is I got just an Allen key that I could just stick onto the spindle, another one that I can line up with it by eye, nice and accurate. Then we can, in the software, go into menu, come down to calibrate, hit go, and so in this mode it's basically at the moment it has a number of pulses that it has recorded off the spindle, so we're just going to reset that to 0. So it's like, okay, rotate 10 times. So I've got RPM turned right down, everything is clear. We're just going to turn it on, and we're going to count basically 9.5 rotations, and then just manually by eye bring it into the last one. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and I just bring this around myself to 10. So once we've done that, it has counted how many pulses it got during the whole thing. I press the set button, and now it recalculates all of the steps per revolution based on how many actual pulses it received during that time. So now if we go back to normal mode. It should be basically the same because I've done that calibration before, but that just means that instead of this having to be perfect every time, we can be a little bit more kind of sympathetic to the machinery and how we set things up, and we don't have to be perfect. We can calibrate. At some point I might improve that even more and provide like a proper sensor. I did think I could just put like an optical sensor and something that passes through it so it can just count it itself, but for now by eye is great. Doing 10 rotations pretty much just allows me to eliminate enough of the noise that we get pretty nice results. That also means that it's very much more general purpose, depending on exactly the rotary encoder you get, what kind of setup you decide to have. If you were using this setup, you could just use exactly the same software, calibrate it, and off you go. So we've calibrated, and now we have all of our range of feeds. All of mine are metric at the moment, except for one. I might add imperial later, because again, we're basically recalculating all of the required pulses every time we calibrate. So it's pretty easy just to have as many different thread types as we want. But let's look at it in operation. We'll start, I guess, with fine feed. And yeah, let's talk about modes first. I currently have basically four modes, I guess. I have normal mode. In normal mode, we set up our thing. Let's just bring you down. So we're on let's bring us all the way down to the lowest possible feed rate. We're in normal mode. So if I start the spindle, see the motor starts spinning, it's just going to maintain the appropriate feed rate. And if I ask for more speed, as I crank up the speed, so does the rotation on the motor. And obviously I can come back down the other way. And obviously in normal mode, if I'm clear, I can engage the carriage let me wait for a turning point, there we go. Engage the carriage, and it is going to move either forwards or backwards, and I have a direction button on here that just flips which way it goes, and I also have these end stops at either end, and I can just dynamically position those, and if the carriage hits into either end stop, then it will also change direction. So if I give it a bit more speed, a bit more pace, and I hit an end stop, then you can see clearly that it just switches direction. So that's normal mode. Relatively standard. Essentially, that's your kind of classic replacement for the gearbox. You can dial in whatever you want on the lead screw and just control it going backwards or forwards. Easy peasy. But then we get into a little bit more interesting modes. So I have a so that was normal mode. We also have surfacing mode. So let's go into surfacing mode. Surfacing mode says, okay, what thread are you set on? So I come back down to an actual surfacing thread. Let's turn that off for a second. So let's just go down to 0.1. So I say, okay, I want to surface this part at 0.1 millimeters per revolution. So that's what I want to do. It's like, okay, move. It says thread start. I use the same. We'll get to the threading in a minute. Basically, move to where you're going to start machining. So I will just manually move the carriage to the location that we want, which is about there. Yep, we're good. And it's like, how far do you want to machine? So let me say, I think we want to machine, let's call that 15 mil. Gauge the carriage onto the lead screw here. We're about where we want to be. Bring ourselves into basically there. I'm going to clean up I happen to know that is at least a 10 mil, so let's clean up 13 mil of it just to get rid of all of that gunk. That should get us past. Perfect. We'll back off. And so in servicing mode now, we're all geared up. We put a cut on, hit OK, start her up, and we will begin moving into position. Very slowly, because this is a very fine feed cut. But the important thing about this surfacing mode is that we're going to arrive at exactly where we expected and then just automatically back off, and it will just sit in a loop going in and out at that pace indefinitely. So there we go, that was our full, I think I styled it for 13 mil worth of clearance. It's a pretty spiffing looking finish, but we've got a little bit of groove at each end from that previous operation, so I will put on another, let's say, 0.2 mil of a cut. What we should see is that on this next pass we hit obviously exactly the same marker. Perfect. There we go. Right, and with that surfacing all done, let's put on some blue dye and move into threading mode. We'll just switch over now and we'll set up for that. From a controller point of view, we walk through pretty much the same wizard, but it behaves slightly differently. We have moved to the start of our thread position, which we can see. We are going to do 10 mil. We are going to, it's prompting me to say, is the tool clear, just so we make sure that we don't crash, and we're just going to show how much of a 10 mil motion is. So we'll come across, and that is a 10 mil worth of thread. How much clearance do I want to come off the end? I will say 5 is fine. That gives me time to adjust in. Probably don't need this much back off. I designed it to be able to back off thinking that at some point you might actually want the back off so that you can get a nut in or something to test fit towards the end, but I'm not going to do that with this. It's not a real thread size at this point. So what we are going to do is we're going to come in to, I guess, essentially a scratch pass. We're going to set the speed a little bit lower. It says, are we okay to start? So I'm going to start up the spindle, and I'm basically just going to press OK on my buttons down here and let it do its business. Ready to cut. Yes. There we go. So we've gone in. I'll just back that out. We will confirm that we've backed out. It's going to move me back to the start point. Going to put that back to where it was, which I think I had it at 0.5. I should have kept better close eye on that. So the important thing here is that obviously I have my compound slide at the right angle, so I've used the cross slide just to come off the cut and then back to where I was starting from, and then I'm going to dial the cross slide to add an actual additional cut on, and when I'm ready I hit go, and it's going to come in, and we'll do another pass, come off, say I'm off, come back to the start point, dial in another cut, hit go, and go. And so basically cutting a thread is as simple as this. Just dial, dial, dial. That means I don't have to worry about stopping. So probably the primary utility here, let's just, I think I've got a little bit of blue dye in there, so let's just do one more pass. Looks good. Come out and we'll close that off. So let's see if we can get you a nice view of those threads. So that is the thread form that we have just cut. And if I bring my thread tool in, hopefully you can see that that is pretty darn good, I would say. Like that last trough is obviously the point of run out, and that is a perfect 1mm thread. So you may be thinking, okay, cool, so it's basically a thread tool, and you can stop, but you can stop whatever. Where I think this becomes super helpful is obviously threading up to a shoulder, like not having to time. The important thing is you don't have to time releasing the carriage, right? You don't have to disengage the carriage. It's just going to stop where you tell it to stop. On an external thread like this, not a massive deal. Where I think it gets interesting, and let's see if I can find a piece for us to do this on, is on internal threads, and specifically like internal blind holes. I find that it could be quite difficult to consistently disengage at the right place, time it right. Yes, I know that you can like turn a tool upside down and like run the lathe in reverse and shenanigans, but we have digital tools to help us. So let's try and do that. Let's do an internal thread. Let me just go find a piece of stock. If I've got a piece of stock big enough, yeah, I mean, I was playing with this chunk before. Let's do that. So I've got this chunk of Delrin that I've been playing with before. It's reasonably sacrificial. So let's see if we can make a internal thread blind hole that matches this. Right. So that's just made a basic hole. Let's bring you back in. So that was a 10mm bit. So that should be clearance for the random scrap, but this isn't going in. So now what we want is to pull that open to about 13. Let's see if we can do that with this. Right, so let's do surfacing. We'll do a relatively quick thread. We are at the start. Oh, let's stop that. That's basically at the, helps if you engage the carriage down. Right, that's basically the start of our surfacing. So I'm going to make an 8mm hole, 8mm depth hole, which is shorter than the thread we cut on this, because what I want to sort of demonstrate, hopefully, is precise threading to a specific depth. So I don't want to necessarily be able to dial it all the way in. I want to be able to get to 8mm in. So let's do that. So yep, that is there. That'll take us in that far. Clearance 5, no worries. Right, so start her up. Give her something. We'll put a bit of a cut on. and we'll just go in. So we've got our boring bar in place, which is going to come in and out. So that was a 10mm hole. I need to get to at least probably 12 and a bit, 12 and a half maybe, to support the internal thread on this. 12 and a half is a bit too small. I think the internal thread needs to be, let's say 13. So I want a 13 hole from which to then dial. So let's put that on, and then we'll see. I'll have a bit of a measure after this one and see where we're at. Right, let's just do that. Just going to take that out of the way for a sec whilst I measure the hole. We're at 12 and a half, so we'll just put another half mil. And then we'll start threading. Yeah, that's a little oversized, but for the purposes of a quick demonstration, I think we're probably all right. Right, so what I want then, and hopefully that's tight. We'll go to threading mode. We will select a 1mm thread, same as we did before. We will jog ourselves into the start of our thread pattern. I think I've overdone that a bit. Let's call that there. So again, we've taken the backlash out. We were heading in this direction. And we will dial in 8, which is how far in we wanted our thread pattern to go. Excellent. And we'll back out 5 again. That seems reasonable. So let's come around to there. There we go. So that's a cut. So we'll come out of it. And we were on 0.5, so let's come into there. We'll dial a bit more cut on. Come out of it. Back to 0.5. Bit more on. And I reckon we're probably good for a test right now. So let's take that all off. Let's grab that off for a second. So hopefully you can see in there. Hopefully in there you can see that we have some threads. The question is, have we opened up enough at this point to fit our previous thread point? And I think the answer is yes, we have. So let me just dial that in. It's a little bit loosey-goosey. I probably could have come a bit more, but that is that. So, but there you see, very quickly, we've developed 2 mating threads that are pretty good looking, I would say. So that is blind hole threading without any drama. No timing carriage lock release, no worrying about whether I'm hitting the same depth every time. Just a nice, clean, perfect thread. This would probably be a slightly nicer fit if I had actually had this as a specific diameter. It was just like a random like 13.6 something or another. I wasn't spending a great deal of time to get precision, but you know, that's a thread, that'll work. So that is probably the most important mode, right? That's why you put an ELS on. To a certain extent, you can dial in all the different thread types you like very quickly, and I think having the ability to have it digitally stop at the exact moment you want is super powerful. Now that does mean, obviously, that the controller needs to be a bit more clever, because when it stops moving the lead screw, it needs to keep count of what the spindle is doing, even though it's not moving. And then if you move the lead screw carriage position, it needs to figure out where in the thread path you are now so that it resumes moving at the right point, which is kind of a digital equivalent of the little thread gauge spinny thing you have on your lathe. Like, you know how a lot of threads tell you have to re-engage at like 1 or 4 or 8 or whatever on your thread pattern. It tells you which numbers you can re-engage on. It's the digital equivalent of that. Like, once you've moved out of position, you have to recalculate a bunch of things. And because there is backlash in the carriage, I had to basically account for the backlash. Now, that's one thing that at the moment isn't configurable, but I will have to make it configurable at some point. I just measured it on my own machine and just added the correct amount of backlash for this particular machine. But given that I do intend to make these available to sell, if anyone is interested in this little box of tricks, then I will make that configurable so you can dial in what backlash you have on yours. That brings us to pattern mode, which is just something else fun that you can do if you're already doing stuff like tracking kind of positional offsets and digitally controlling things. So let's have a play with pattern mode. All right, so we're going very slowly. We'll just pull in to put a light cut on at this end, so we have a nice little fine cut, and we will hit go. We interrupt this video. You are 25 minutes in, and I'm just going to ask a favour. If you got this far and you're watching, drop a comment, something, just say hello, wave, let me know that you are not a bot, that the traffic that comes to these videos is actual people, and that it is in fact worth me spending all this time filming and editing because humans are watching, because it's not always obvious. So if you could do that for me, that'd be great. Thanks. And there we have our basic pattern. And furthermore, what we can do is it's sitting here saying, do I want to go again? So if I start this going again, I can put a bit more of a cut on. I've got to be careful because obviously it's got to have the power to do the cut, but let's try this. So we should go exactly back over where we just were, but making deep cuts. And that, my friends, is pattern mode. Right, just going to clear off that surface, just in normal mode. See whether or not we can clear it all up in one go, and then we'll reset and do another pattern. Now we can do bi-directional patterns and single directional patterns. I'm going to dial in a single directional pattern. Right, so we'll just engage the cutter a little bit, turn on the lead screw. Okay, so we cut our first path. Need a little bit more on there just to cut all the way around. Cool. So now it's like, are you ready? So I'm going to back the tool out and say, yep, I'm ready. And now I'm going to put the cut back on, so we'll get a ring at this side as well. Let's just make sure that's pretty clean all the way around. Okay, now I'm ready for it to do its next pass. Press the button.
It engages the cutter at the right place. Back off. Come back. And just clear some of that out of the way. Put the cut back on. Tell it that I'm ready. Back off. And that is simple as that. We now have 3 spaced spirals.
And that is that, basically. A fairly cheap encoder, a relatively expensive motor, and a little bit of brain wizarding on an Arduino Nano, and you've got yourself a funky little electronic lead screw. I hope you enjoyed that. If you have any other ideas for interesting modes that it should try and do, let me know. If you actually think you would be interested in having such a capability on your lathe, also let me know. As I said earlier, I am considering selling them. I have a few spare PCBs already. If there's enough interest, I will try and do something about that. Other than that though, thanks for watching. Hope it was interesting. See you next time.